Yes, looks good.
Okay, great. Okay, so thank you for giving me the chance to talk to you guys about this analysis description language project. It was actually initiated by Cezanne many years ago and sort of developed at LINQ. So what I thought I would do today, rather than talking details of syntax and so on, which in any case is still under development, I'd like to really concentrate on sort of the basic idea and the motivation for this. I think that would be more useful, since we shall be having a workshop in May where such details will be discussed at length. I think we all agree that one of the primary goals is to maximize the impact of the LHC. If you look at the European strategy and as well as P5, everyone agrees that that's what we should do. And so anything that can be done to that end is, of course, very important. One of the things, of course, is to make data accessible. After all, having spent so much money and time getting these data, we actually want to make sure that they're available well into the future. We also would like to make simulations of various kinds available, Delve, Buckfire, Falcon, and so on, so that people can use these data in some sensible way, as well as results. And as we well know, there's a lot of effort to put data into various databases, such as HEP data. And the other thing, of course, is to make analyses also available in some fashion. And as you well know, there are many initiatives which are ongoing, not least of which the initiative at CERN to preserve analyses. And so what I want to talk about today is one initiative that entails something called the analysis description language. So before I do that, let me just say a word or two about something called domain-specific languages. Now, of course, every discipline like ours, we have our own concepts, our own way of thinking about things, and our own way of solving problems in particle physics. And the history has been, of course, in particle physics is that we've generally solved our problems using some sort of general purpose language. First Fortran, now, of course, C++ and Python, and no doubt there was something else in the future. And of course, we do that because, a general purpose language has the virtue that in principle it can solve a very large class of problems. It may well be in some cases that one has to work very hard to solve a problem, but in principle it can be done. The disadvantage, of course, is that such languages do not model how we think about our field and how we do analyses. They're not designed for that purpose. They are for all general purpose. And so this is why in many domains, people have invented somewhat limited languages called domain-specific languages, which are designed to model how the domain expert thinks about her or his field and how those problems in that field are solved. And so the idea is to essentially use this idea to develop a language that can describe analyses for the LHC. And so the way we sort of think about it is that an analysis description language is just a language specific to particle physics in this case, that is designed to describe the content of an analysis in an unambiguous way. And by the content, we might imagine that that would include the object and event selections, the definition of objects and how objects are transformed one into the other. It would also presumably describe both analytically and algorithmically observables, for example, the RISD observables, including those based on machine learning, efficiency maps, etc. Essentially all the elements that comprise analyses at the LHC. And of course, the other reason for building such languages is that because they're designed to model the way we think about our field, in our case, HEP, then they're designed so that anyone who has an interest in or knowledge of HEP physics can use that language to, to visualize, validate, combine, reproduce, interpret, etc. The analyses at the LHC. Now, we, of course, have some experience in simpler versions of this in particle physics, the so-called LINQ event code, SUSY LINQ code, and so on. So we do have sort of prototypes of this approach. We want to essentially extend that to analyses. And indeed, actually, way back in 2015 at LINQ, there was a very extensive discussion about analysis description languages, and in particular, we call this analysis description accord, some kind of agreement by the participants who are listed here. And in fact, in the proceedings, we actually wrote up that preliminary accord about what a language, analysis description language, might entail. And since then, there's been various workshops and discussions about moving that forward. One of the key aspects of any kind of limited language is really to design and decide upon the scope of that language. That's very important, and it's very important to get that right. If it's too large, then of course it's self-defeating. One might as well just go back to using a full-fledged GPL, general purpose language. If it's too narrow, then it won't be used because it won't be sufficiently expressive. And so getting the scope correct is actually very important, and that requires a lot of discussion. But in our view, sort of the core of any analysis description language for use at the LHC should include, presumably, object definitions, observable definitions, definition of event selections, and ideally, standard reports and visualizations of analyses. Now, of course, there are lots of other things that we do, background estimation, scale factor derivations, etc. And of course, there are things that we cannot anticipate that we shall be doing over the next 25 years. And so, of course, these things are not yet included in the scope. But one thing we would like to ensure is that the core is designed in such a way that if and when extensions are required, they can be added without breaking the core. So what are the properties that we, in our discussions at various workshops, including at LINQ, we have arrived at? Well, the basic requirement is that this thing has to be public. Right? We want everyone to be able to access it. It has to be complete in the sense that it covers a very large fraction of the analysis that we can imagine that one might want to do at the LHC. It will fail miserably, of course, if it's not something that can be easily learned. And so one has to be very careful at the semantics of the language, how it's designed, so that it really feels natural to the physicist. And there has to be a way to demonstrate its correctness. That's something that's very important. Other desirable features are that it should be self-contained, it should be independent of some underlying programming language, because languages change, right? We used to work with Fortran, and now we're with C++, and who knows what's going to be the language of the field 20 years hence. And it should be independent of any particular analysis framework, and I'll get to that point a bit later. And so what we shall do now, I'm going to focus on a specific proposal that was made based on the discussions at LINQ in 2015 and subsequent workshops. And of course, the question to be asked is, what's a good way to organize the components of an analysis? And one thing that that we already know about and have used successfully is using sort of block structures to define sort of entities, such as in our case, you'll see objects like electrons or what have you. And such blocks have been used, as you well know, before, for example, in the SLHA or LHE formats that were developed some time ago. And so, based upon this sort of general notion of blocks that define certain constructs within the language, we actually wrote a proposal with a specific idea in mind, and so this proposal is available, and that's essentially what we shall be talking about for the rest of this talk. So after this paper was published, or at least put on the archive, with a specific proposal for an ADL. We had a workshop in 2016, in November 2016 at CERN, to develop the ADL sort of syntax a bit further and to have more discussion. And that workshop, it was decided that really the only way to make real progress was to actually try to implement proofs of principle of this idea, by which we meant programs that could take this language and actually do something with it, such as running actual analysis. And so there are essentially two approaches that that have been tried. And actually, the second approach, the interpreter, actually came first, which was essentially a runtime interpretation of the ADL. And because it came first, its syntax is somewhat different from the syntax that was developed in the proposal that on the previous slide. But basically, there are these two approaches. One, the so-called transpiler approach. That is to say, one takes one language and converts it into another language. In this case, one takes the ADL and converts it into C++, that can then be compiled and plugged into some framework. And there are essentially three sort of proofs of principle, and I refer to them as proofs of principle because I think there's still some work to be done to really make them robust, etc. But we thought it was important to get to this point where we can actually show that this idea actually makes sense and works. And so there is something to basically fit into the Rivet framework, and something called the TNM and Checkmate. And again, the idea is that the ADL itself is completely independent of the framework. However, it can then be translated into something that can go into a framework if one wishes. And the other approach, as I mentioned, is the interpreter, the runtime interpretation directly of the ADL, developed by Gurkan, called Cutlang. And as I mentioned, this was the first really first attempt at showing that this whole thing actually works. And so after this, we thought that the way to proceed was to actually look at a set of Atlas and CMS analyses that have been published and actually implement them. And that is to say, write these analyses in the ADL or ADLs, and test them by running these either transpilers or the Cutlang interpreter on these ADLs, and show that we get results that are meaningful. And indeed, what was done was to take the examples from the 2017 LINQ reinterpretation tools workshop that basically use the DELF samples, and just show that this thing actually works. And in fact, there's actually a short note. If you go to the LINQ 2017 proceedings, you'll see some description about what was done. And in fact, the results were presented at a reinterpretation workshop at CERN subsequently. And so that's the approach. The approach is that, you know, here's a language with some idea about how it should be constructed. Actually write analyses in this language, run these various tools to either translate from ADL to C++ and subsequently into a framework, or to interpret and then see whether this really works. That's essentially the approach that we've taken. And in fact, the good news is that this actually worked. These tools actually were able to run on these analyses, producing results and so on. And in fact, Cutlang went further, and there's actually a publication that describes in more detail this successful outcome. One of the things that is very important, and this still needs to be done for the other approaches, is to make these tools much more robust. And in fact, a great step was taken actually not too long ago with Cutlang, in which it was basically rebuilt using LEX YAC based tools for parsing in order to make the parsing of these files much more robust. Other developments that occurred was some, adapting one of these tools, this so-called ladder to TNM, to handle the CMS nano AODs. And again, this is something that's happening to the other tools as well. So let me just say a little bit about, again, I don't want to go into details about syntax because, this is still developing, still being discussed, and we want to make some real headway in the May workshop to try to sort of pin things down before we can actually say that we are ready to build something that's robust that can then be released to people to use. And so I just want to give a kind of a general overview of what was proposed in this paper that was mentioned some slides ago. And so the most important thing that we decided that the things we should focus on are, one, that the ADL should be human readable. That is, it has to be something that was relatively easy to understand and to write. Again, it has to be independent of any particular computer language, and it has to be independent of analysis framework. Now, there are some people, of course, who see this and they get worried. They say, oh my goodness, independent of analysis framework, but I have a framework, so how can that be? But the point is this, is that the ADL is independent of analysis framework precisely so that it can be an input to such frameworks, rather as is the case for the SHA files, which are standard inputs to SUSY calculators. And in fact, it's my view, and I think that's shared by many, that we should simply accept, the reality, which I think is healthy, that a physicist will work with whatever framework he or she judges to be the easiest. And presumably by the time that the LHC era is coming to a close, but we should still be analyzing LHC data in the 2040s, today's frameworks may well be considered obsolete by then. But the hope, of course, is that whatever ADL we finally focus upon will not be obsolete and will still be able to describe the analysis that have been done prior to the 2040s. So what is this proposed ADL? Well, it's basically just a plain text file that describes an HEP-specific language with rules that we hope are robust and sufficiently expressive to express what we wish to do in analyses and have done in analyses. And of course, those rules include standard mathematical and Boolean operations and four-vector algebra. And again, the key is getting the scope right. We don't want to go so far that it basically just becomes another GPL, general purpose language, but it has to be sufficiently expressive to make it useful. However, of course, we expect, and that is really the case, that there will be many variables that are quite complicated to describe in such a language. And the thought is that such variables will be encapsulated in functions in some function library that can be accessed. And that's very important. For example, if you wish to create variables such as the razor variables that involve some algorithmic manipulation of objects in the event, and it would make sense to have that be a function. Just as we are now, after many, many years of writing our own thing, I remember in D0 and other places, we would write our own jet finders. But of course, eventually, everyone converged to using some standard jet making libraries, and that's what we expect will happen here too.
Harrison?
Yes.
Yeah, this is Gordon. This library with the self-contained functions, is that written in a particular language? Does the ADL, is it expressive enough to write those functions, or
so that's a very good,
that done?
Yes. So that's a very good question. The thought is this: is that these things were written in whatever language people deem to be appropriate, let's say C++, what have you. The ADL itself will describe the names of the function to be called, but how the tool that reads the ADL does the binding to those functions is up to the tool, not the ADL.
Okay, so this is the way you let the abstraction leak in a controlled way.
Yes, exactly.
Okay,
yeah.
Perfect. Thank you.
Okay, thanks for the question. Any other questions, by the way? Please do interrupt. Okay, so what is the core of this language? So let me first of all start by saying, when you sort of step back and look at our analyses, what does one see? One sees basically objects that transform one to the other and manipulated in various ways. And then having built these objects, and one views the event as an object on which certain selection criteria are applied. And so we sort of felt, basically having easy to read blocks where blocks define objects it would be a way forward. And so this is really a structure that is a block structure with a key value elements where the value can be quite complicated, right? It could be some very complicated Boolean system. It could be a call to some function, an assignment, or what have you. But the idea being that the block type defines, is defined by this key value sequence of statements. And the other thing is to try to have a clear separation of the analysis components. Now, again, if you read a typical paper, if it's well written, then you see that there's a clear separation in the analysis components. But often, we tend to get things all tangled. And so one of the goals here is that is to have a way to standardize the writing of the description of these languages. And the thought is that if you have this block structure, that will help to impose this kind of standardization. Of course, the key can appear many, many times in different places. And the current version includes the following block types. Info, again, I want, in a backup, there are some preliminary versions of these things, but the main thing I want to focus on is just the overall big picture. There's a block that describes information about the analysis, details about the DOI and so on. There's a block that describes functions, and this is where one would describe which functions, external functions, can be called, but then the binding of the function is the responsibility of whatever tool takes in the ADL and does something with it. There is a block called object, whose purpose is to basically be the thing that describes the transformation, the creation of an object type. So, for example, you may have an object that is basically a list of things called electrons, and the output of the block might be clean electrons. And so the block will describe how electrons are transformed into clean electrons, for example, and so on. And the other important block is a cut. So having defined all the objects of various kinds, and of course, objects, and by objects, we can mean anything. So as you well know, there are people looking very closely at dispensing with even electrons and actually going all the way down to cell level data in analyses, the so-called end-to-end analyses. And so we have to be very flexible about what we mean by an object in this case. But the point is that the object is the thing that describes how that object has been created from other objects. And then having done so, the cut describes what selection criteria are applied to the event, and presumably those the objects there could be just variables, observables, as well as variables that are bound to objects previously defined.
Harrison?
Yes.
I'm sorry to interrupt again.
No, please do.
Yeah, so I cheated and went way forward to the end and
Yeah.
just looked at some of these, and I definitely recommend other people do because it makes it pretty clear what Harrison is talking about. But it looks to me like objects contains cuts as well, just cuts on the object, and so cut is strictly an event level. Is that or multiple
That,
object?
that's correct. Yes. Yes.
Okay.
Yeah.
Yeah.
Let me comment on this. Actually, yeah, what Harrison has in the backup is, definitely not final, and it's under development. There are different approaches, different syntaxes that are proposed, and cut is one name which we don't like that much, so it can change. It will have to change.
Oh yeah,
So
no,
just
no.
look at them, but yeah, more just to get an idea, not.
Yeah, exactly. I didn't imply. I said didn't mean to imply any criticism at all. I'm
No,
just
no,
trying
no.
to understand how these
Yeah,
pieces fit together.
no,
Yeah.
I just
So
wanted
that's
to
why.
make a comment for the whole audience.
Right. So that's why I put in at the very back of the slides, where we are right now, recognizing that this is completely fluid, and it's important. And actually, this is actually one of the important things we want to really pursue and discuss at the May workshop is are the names. Are the names do they express the concept that we wish to express? And you're quite right. The object contains cuts, and so the word cut does not seem to be perfectly appropriate, since these things are selection criteria applied to higher level objects, i.e., events. So points well taken. And there are, of course, various keywords, which again are ones that can be discussed and debated. If I go to now where we are right now, so there are these current projects, right? There are.
I apologize, Harrison. I have one more question related to these
Gordon, no need to apologize. Please stop me at any point.
Okay, so so one of the things that happens in a full-blown analysis in a general programming language, right, is we have an order in which we apply the cuts.
Right.
And this order is often dictated a bit by the signal. It's sometimes dictated by the reviewers. Right. There's all sorts of people who put pressures on an analysis and how they present that information. And here is the order in which things are applied. Is it basically driven by data flow? The system starts with whatever the result is, and then it says, oh, to do this result, I need these variables, which means I need these objects, which, going back, is that?
Yeah, so that's right. So in fact, that's actually a very good question, because the actual order of blocks and so on within the file is quite, at least ideally should be irrelevant. Because what should happen is that the blocks automatically form a tree structure, right? Because you'll have, for example, clean electrons depend on electrons, and so on. And so there's actually an implied tree relationship, and that's something that. Sorry?
A tree or a DAG, directed acyclic graph.
DAG in one. Yeah. And so that's right. I mean, this is sort of the what's implied, and I think again, my view is that those sort of things should be whatever takes the ADL should be clever enough to actually do the right thing to build this DAG. Right. Essentially data flow, yes. And the important point is to model the way physicists actually think about, well, it's two things actually. Model the way we think about our analyses, but also to try to encourage people to think about analysis in a more streamlined, coherent fashion. So there are two, there are in fact these two goals. We certainly should model how people think, but we should also try to encourage people to think more clearly about what they're doing. So what are the current projects? Well, there are two sort of approaches. As I mentioned, there's the so-called transpilers. You take the ADL and you spit out some C++, which is then compiled and into some framework. And there's one for Rivet, something called TNM and Checkmate. And then there's the interpreters, of which right now there is only one, and that was actually the first sort of proof of principle that this whole thing really works, this so-called runtime interpretation by Gherkin. And in fact, Kotlin, as I said, it is based upon the principles that were subsequently converged upon at these various workshops, but the syntax is somewhat different. That's because this actually preceded any of this subsequent work. So I'll just say, briefly a little bit about each of these things. So this Rivet-based system, again, is just a Python program that basically reads the ADL and spits out code that can then be plugged into Rivet. And you see, you can have a look and see where that is, something about that code in that this website, and it's largely to be used for pheno analyses, right? That's essentially the main target audience, and it needs further testing. And I'm not sure exactly what the status is right now, but it's something that the people who are involved in Rivet seem to be quite interested in actually pursuing. The other transpiler is this thing that Cezanne and I worked on, that again takes an ADL and creates C++ from it automatically, and then that code is then compiled and run within this framework called the N-tuple maker, which is some sort of generic flat N-tuple analysis framework that depends only on root. Now, one of the things that I think both Gherkin and us, we realize is that if you actually want to build something that takes some ADL and then prints out, C++ or whatever, then that thing has to be able to implement the analysis using some type, and so there is this question about, let's say you would like ideally an analysis developed by Gordon with his own peculiar types with certain attributes. That analysis may be very nice. You may want to run it either on Atlas or on CMS, but it may well be that the data input does not have particular attributes. And so there has to be a way to somehow extend types within the system, and so this is something that that this particular transpiler tries to do. Why am I saying that? The reason I'm saying that is because maybe this is too ambitious, but one of the visions we have is that analyses become commodities that can be run. Whether you develop one, it develops in Atlas or CMS. It would be wonderful if we arrived at a point where we could run an Atlas analysis on CMS and vice versa. That's sort of the vision that we have. One of the problems right now with, well, not problems, but one of the limitations of this particular prototype is that it's basically built by hand, and it would be, we are now assessing the effort required to actually rebuild this using a formal grammar for the ADL and using tools such as PLY. And in fact, Jim has been very helpful in this regard in trying to teach us how to do all this sort of thing. There's this thing, there's also a similar sort of tool to go to Checkmate, and in fact it's been exercised on the knowledge analysis from Atlas, and it's also tested some simple version of the automatic function download, rather like what happens in the language R. So if you've ever used R, you know that there's a nice system by which it will go off onto the web somewhere and download modules that are needed for an analysis, and so this some sort of simple version of that has been tested by Daniel. And finally, we come to Kotlin, which is the one and only interpreter. So this is a runtime interpreter that directly interprets the ADL. And as I mentioned before, this tool adheres to the ADL principle, but since its development began before the Accord as developed at Les Houches, its syntax is somewhat different in detail from that of the Accord. But work is underway to try to see whether there's a way to converge and bring the two together. Moreover, Erlang has some special features that enhance the runtime interpretation of the system. And what is particularly interesting is that it's currently works with multiple data formats from Atlas and CMS, Delph, etc. And it's designed in such a way that more can be added. And unlike the other prototypes, this one has actually been used on a real Atlas analysis. So we really got to the point where one can show that this approach really can be used in real life. And the other thing that was very good was that it was basically rebuilt to use much more formal parsing tools such as Lex and Yak, and actually has been fully documented. Okay, so I'm coming to the end. So one of the things that's important, of course, is that we should have to recognize there are many initiatives to preserve analyses, etc., happening, and there's, of course, this major effort at CERN. Now, we've actually talked to these people, and they are very supportive of the idea of an ADL and tell us that such a thing can be easily incorporated into their system in order to store these files, self-contained functions, and so on. And so there's great support from that side, which is actually very encouraging. So, summary and plans. Well, summary. We are of the opinion that that developing a domain-specific language for our field for analyses, whose principal role is to be able to describe analysis at the LHC, has a role to play, and we are well on our way towards such an ADL. Indeed, an ADL exists. In fact, two of them exist, and they have been run on several representative analyses. That is to say, we actually read the papers, implemented the analyses with these ADLs, run them through these various transpilers and interpreters to show that basically we get the same answer. Now, what is incredibly important to us is that this is an open project, and therefore we are very, very, very much eager to have people come in, critique things, make suggestions, help to basically build something that actually will be used by people. So this is very, very important. The good thing is that this ADL concept is gaining some traction within the community. As I mentioned, the CERN preservation group are very keen on the idea. And indeed, we shall be having a workshop in May at the LPC to further the process. And it's quite clear, however, that this is time, we now need to have a much more expert discussion about details, making concrete decisions about minute details in order to really make headway, and that's one of the goals I hope of the workshop in May. So that's what I have. Thank you.
Okay, thanks. Are there any questions in the room?
Can I ask a question?
Mm-hmm. Yes, please.
Thank you, Harrison, for a very interesting talk. My name is Yuka Takashi. If I understand correctly, the all ongoing project that the transpilers and interpreters that you mentioned are using some amount of C++ layer or calling it API or library, right? Mm. I guess the advantage of the approach is that you can utilize the existing C++ data analysis framework, namely root. But I guess the downside of this approach is that you need to inherit the technical debt from C++ and the existing frameworks. For example, outdated source code, test, and most notably the performance overhead. And I would like to ask, how do you think you can avoid inheriting those technical debts from old source code?
Okay, so if I have answered you correctly, the question is, let's fast forward to 2040, when C++ is no longer, in use. Things have changed radically, how are we going to cope with that, right? Well, one thing that's important to understand is that the ADL is designed to be independent of whatever target language or framework exists, precisely because we cannot anticipate how things will change. And you're right, in the current transpilers and the current interpreter, they basically use the existing libraries. So, for example, root, right? Because root has this this class that exports lots of four-vector algebra, and it made no sense to rewrite that ourselves. But who knows? That might change. It was very likely to change over the next 25 years. But so long as the language itself is completely agnostic with respect to the target language, we think there should not be a problem. The problem will only arise if the language becomes tied to a particular module or package or language. Then that would completely break the idea. But it has to be completely independent.
Okay, so you're like aiming more the future, and you're kind of like designing the front end, which is which has a higher usability for physicists, like rather than like trying to implement the original backend. So this is like a prototype.
Exactly.
Front end, yeah. Okay. Thank you.
Maybe I can say a few things about that. This is Gökhan here. We did a comparison of the performance implementing the same analysis, say top reconstruction, in fully hadronic mode using the CMS and Atlas open data. Of course, open data is based on root entuples. Obviously, between Atlas and CMS, root file is a root file and nothing changes. The impact of having a fully interpreted language is about, say, 10% on the performance when you process something like 50,000 events on my laptop.
Okay.
10%
10%
compared to pure C++ implementation.
Okay.
The difference between C++ and interpreted version. I am sure the version that produces a good C++ file, what the transpiler lists, they are performing better. Now,
actually, let's. It's probably a good idea to move on to Gordon's talk. Otherwise, we're going to run out of time because we're getting very squeezed at the end.
I'm sorry.
Yeah.
Sure.
Okay. Thank you.
So let me unshare.
Maybe just one comment on the very last comment on this. Of course, there's much room for optimization in the interpreter approach, and still without the optimization, it's 10%. So it's already a very good start.
I see. Very good.
So have I unshared?
Not yet.
Okay.
Yes, now you've done it. And Gordon is now sharing. Okay, thanks. No, further.
Okay. Oh, sorry. Can you? Okay. So I just wanted to say, following on that conversation that was just happening, my experience has been that these things add very little overhead as soon as you get to more than, say, 10 or 15 events. By the time you're processing tens of thousands or hundreds of thousands of events, these different approaches make almost no difference. If you're just trying to look at 10 events for something quick, then then at least in my experience, you notice the overhead for these sorts of things. By the way, on my local screen here, video is implying half my slide is cut off. Is that the case for others, or can they see all the way over to the edge, like in the upper? You can see the whole thing. Okay, good. Okay, so I wrote this talk at a more detailed level than Harrison did. So what I'm going to do is skip the details, especially considering the time, and concentrate mostly on the high-level discussion. But there's lots of details in here. I'm talking about a project called LINQ to Root, which is, that's not lint, I misspelled the first T there, it should be a Q. This is a project that's been used in a number of public atlas analyses, both papers and conference notes. So you have to excuse the style of this talk. I got started and then I couldn't stop myself. Don't download the PowerPoint, it's huge. This project's based on an idea of something called a declarative analysis, and I'll show you how this sort of fits into this landscape that Harrison talked about in a minute. And the idea behind it is, much like the ADL, is you specify what you want to do it, but not how you want to do it. The first one that became a real programming language that I'm aware of is something probably everybody's heard of called SQL. And it was based on a fairly formal CS paper in 1970, and SQL has been around since the early 70s as a result. And it was just an experimental language in somebody's, not laptop back then, but computer account, which then, of course, has blossomed into this huge industry. So slide 3. So the idea is, instead of operating at the analysis level, operates at the plot level, say, or some sort of result object level. So for example, if you wanted to plot the missing ET for events with 2 jets with PT greater than 40, and each of those jets having at least 2 GeV tracks within a delta R of 0.2 of the jet axis, but you want to do it for all the data that we have accumulated for run 2. And of course, this means that the project needs to be able to deal with your data model. Harrison made references to this, talking about Atlas or CMS, has to be able to deal with some significant CPU resources, potentially GPU resources as we move to these more modern ways of doing, of processing large arrays of vectors. And of course, the inevitable, where is my data that I want to use? I want to just be able to say run to data, and then I don't want to care about where the thousands and thousands of files are actually there. And as a result, you'll get out some sort of a plot. I used the CDF plot, harking back to when I was a grad student. Sorry, Harrison, I should have put a D0 plot in there.
It's okay, I'll let you off.
Both Harrison and I were on D0 in a previous or perhaps current lifetime. So slide 4, I just wanted to quickly break down what one of these requests are for a particular plot or thing. So there's an action, which is you've got to know how to plot now, or maybe you want to build a T-tree or create a pandas data frame because you need to use the scikit-learn training tools, or a CSV, or something new that comes along in the next decade or 2. Then you've got to figure out what it is you're trying to plot or fill, or etc. I'm just calling this loosely the target. It could be all sorts of different things. And then, of course, there's the selection, which is perhaps the most complicated. Note that in this very simple statement, there's many implied loops, looping over events, looping over jets, looping over tracks, and you have to match between these various loops. So if you were to write out the C++ code here, it'd be a bunch of nested loops with a bunch of if statements, and you'd be caching some calculated values, etc. And then, of course, you would like to be able to add the word calibrated everywhere, because who doesn't want to use calibrated objects? And of course, that implies in all the experiments quite a bit of background. Quite a bit of extra machinery coming in. Okay, so I'll skip this slide 5 and just go directly to slide 6. And I'm going to be late for my next meeting, which is okay because I'm the convener. So if we look at the grand scheme of things, starting from production analysis files and going all the way to publication, both ADL and this sort of fit somewhere in the in the middle there, where you're scanning the data, fitting, machine learning, and then getting a result. So one difference I noticed between what Harrison was talking about, what I'm talking about here, is that the idea here is built into it is exploring the data, making certain plots, whereas the ADL is, at least at my first blush, and I apologize, Harrison, for not being better versed in this, organized around an analysis, around a paper. whereas this is organized around building up the components for an analysis. So it exists in a different place in the layer cake, which I actually have here. So at the lowest level, we have the data files. At the second level, we have some sort of structured query. So our data frame, I mean, even T-Tree Draw, NumPy, Pandas, LINQ, this LINQ project, all exist at this level. And then above it is some sort of query or set of operations which has knowledge about the domain. So the structured query, you could use this in a nuclear physics experiment as well as any of these tools in a nuclear physics experiment as well as a particle physics. When you have domain knowledge built directly into things, then it's less of an opportunity. And ADL somehow spans, I think, those top two, where its foot is more firmly in the top one, and the LINQ project I'm talking about spans those top two also, but its foot is more firmly in the structured query. So these are slightly different things. So I thought I'd just quickly show you what this looked like. I chose a language because of a set of language features, but that's neither here nor there because you can't. This is basically the ideas behind this are language independent. But the idea is that you take a set of events, you select, say, for event weights here, and then you make a plot. And then you save the plot to a file. So key things to note are that there's no explicit loop. This particular version runs on root T-trees, even though you never see the declaration of a root object anywhere in your source file. Let's say we do something more complicated, sort of like that query I posted at the top. To start with events, and then you ask to only look at events where jets have a PT greater than 40 and where they're tracks with a delta R less than 0.2, where there are at least two of those. And you see I had to use a delta R squared function. I was too lazy to write that correctly myself, so I wanted to use a particular root library. This is like the function table that Harrison was talking about a little bit earlier. So if the event passes that, then we select the missing ET, and then we make the plot, as you see there, and then save it. So a couple of things to notice about this. One is there are actually 3 implied loops, but nowhere is the loop code written. And the idea behind this is that the backend will know better how to do this, depending upon the data, where it's located, and how it's written out. It will know better how to write the loops. And this also means you're agnostic to the type of data. This is meant to express the intent, not how to actually go about grabbing it. Also note that the final product of this is a plot, for example, not anything else in particular, like some sort of full-blown sequence. So it's very different from the data-driven way that Harrison was talking about in that sense. Okay, I'm going to skip this slide, which just talks about the various operations. The main thing to think of when you think of this as in a model is that we operate on sequences of events, sequences of jets, sequences of tracks, sequences of floating point numbers like the missing ET. So everything is done by sequences on sequences here. And there have been many computer science theory papers written about what sets of operations you need on sequences in order to be able to do everything that you'd want for manipulating that kind of structured data. And it turns out in an actual analysis, at least the ones I've done, which is a very small subset of all possible analyses, these were the operations that I needed. But I will leave them for you to take a look at later. There is a data flow, the way the system works. There's a user interface, which in this particular case is a general programming language, which I'll discuss in a moment. And then there's backend, which I'm going to go over. I'm not really going to go over it all. There are slides for all of these, but I'm going to skip them. There's just 1 or 2 things that I wanted to point out. One is that this is designed so that you can ship a query for a plot or multiple plots over the wire to some backend facility. And the other is this idea of a cache, which means if you've done exactly this before, why waste time running on the data files again? Just go get me that previous result. There's more information about all of these components further in, but for the purposes of this talk and the time, I'll skip it. One thing I did want to say, I think the user interface, which is how the physicist manipulates the data, I agree with Harrison here. It has to be all text. I've done a couple of approaches before I said this is the third version of this framework. The first version, excuse me, was a bunch of, I actually tried to do a GUI. That's just not flexible enough. And also with modern source control, you really want text so you can do differences. There are a number of big, I think really strong points behind doing text. The second thing is the second version had a set of text files which were kind of similar to what the ADL was doing, not exactly the same. Where I described cuts, I described how to put objects together, things like that. And I always discovered I wanted some new operation. And that operation then meant I had to write a function in a general programming language. And at some point, it started to get hard for me to track all the leaps from one to the other. I like the way ADL has done this. It's a better way of doing it than I certainly had. But my experience led me to the conclusion that actually we want a DSL that's embedded in a full-blown programming language. So I settled on C# because when I started this project 6 or 7 years ago, it was the only language out there that had enough power in order to do this. It provides for the leaky abstraction, as I've already said, and I was also able to make thousands of plots in a run, and it would, if the caching worked well, so that would take 3 or 4 minutes if you made those plots already. The other thing I really liked about C#, of course, was it was strongly typed, but that's a personal preference. Okay, so I wanted to make a little bit of an emphasis on the user interface for the analysis here, because I think this is one thing we'll have to address as we go forward. As we run on larger and larger data sets, we'll want people to have less options so we can optimize the back end better. Of course, as being a physicist, we all want as many options as possible. Okay, I'm going to skip slide 13, although and 14. I'm totally open to questions later on, as well as 15 and 16, which is discussing how to find your data files and make it easy, and then 17. And I wanted to just mention 18, and then I'll get to my final slide if I remember right. So this was written in C#, which is a fantastic language, but has not got wide adoption in particle physics. The obvious thing to try it out in is Python. C++ is another possibility, of course. So the question is can a language like this one drive an XAOD, which is a structured root format in Atlas, which requires a large number of libraries to properly read? It's not just a flat T-tree. So can a similar language drive something like that? An analysis on a flat T-tree and a columnar analysis. It's based on data structures like pandas or awkward arrays or similar. I'm quite confident of the first two, and the last one is something that would be good to answer, because that shows that this is really independent. It's really data format agnostic, this approach of expressing what we want to do. I've started a project along these lines. I'll just say that what I've got currently, which I link below and people are welcome to look at, is written in Python, but it's using C# idioms at the moment, and this is just because I don't know all the ins and outs of Python yet. You can see there's actually a small Jupyter notebook which will run on an Atlas XAOD and extract a column of numbers, namely JetPTs. It's a very simple thing, and it can't really do much more than that. It was coded just to do that. It's heading towards a goal for a particular physics analysis I'm working on. But the two people working with me, Emma and Mason, are joining me to help see if we can answer some of these other questions on a very short time scale. So just finally, I'm a firm believer in this approach, but it's definitely not without its problems. When you take away flexibility, people get annoyed for good reason. On the other hand, it makes it very easy to do things the framework is aligned with. The question is, as Harrison was saying, can we make sure to hit the sweet spot so that 80% of the people like something like this, and the other 20% are frustrated enough to add the extra features that are needed, as opposed to just everybody moving back to something like C++ or Python. I do think because of the size of Run 2, we're going to have to move to splitting the analysis in the server. I don't think I really need to say any of this. This is sort of aimed at a longer talk than we have had time for, I'm afraid. So that's all I've got for this, is a basic introduction to this idea of doing declarative analysis, which is, fits in. I could imagine the ADL being mapped into something like this, for example, from what little I know of it. So it fits in at a different layer than the ADL does that Harrison was talking about. All right, thanks.
Thank
you. So if I can just ask one question before you dash off. So you mentioned that I think it's a very good thing that this whole approach is completely agnostic with respect to the particular language, C#, what have you. So today, if you had to choose another language, are there such languages that are similar to C# but are better?
So if I had to remake this choice today, yeah. So the answer, it depends a little bit. So one of my personal preferences is I very much like strongly typed languages. And at the moment, there are 2 features in C#, which is strongly typed, that I'm not aware of in any other language. A functional language, like some OCaml-based beast, might be a possibility, and that's because one of the big pain points with C# is that when you ask for 1,000 plots and you want to manipulate those 1,000 plots, being able to do that in a transparent way is not trivial. This gets into something I like to call monad hell, and I really need a couple of slides to explain in detail what I'm talking about here. Python, for example, is much better at that. It's strongly typed, which helps. So Python is good, and one thing about Python, there's this user interface concept, and then there's this idea of expressing, in a computer-friendly format what you want to do, and the user interface should be physicist-focused, and then the data structures that tell you how you want to actually manipulate and make plots should be computer-focused, if you will. And in Python has a different set of idioms for expressing things. Like, for example, in NumPy, one of the common Python packages, there's a very concise way to specify a cut. And there's no reason that can't be mapped onto something like this. I don't know enough about Python yet to know how to do that properly in Python.
Yeah, so just a comment, actually. So I really like, one thing I must say I really like about this approach that you've been pursuing is that I've often thought that there is a big lack in our field, which is somehow a way to simply query the data, just to explore, in a very simple way that doesn't require a huge amount of expertise. And it seems to me that is partly why I think something like that actually would be extremely useful.
So this is exactly one of the main motivations, is to make the t-tree draw function a bit more formal. And you would never use t-tree draw in your final analysis. It's way too inefficient. But why not design something which is close to t-tree draw that you can use both to explore and in your final analysis? And that was one of the design goals of this whole project.
Yeah. Okay. So will you be attending the May workshop, by the way?
I'm going to try to attend that workshop. At the moment, I don't think there's any reason I can't, but having a family, sometimes things come up.
Yes, indeed. Okay.
Okay. Are there any, I realize it's late. Are there any last questions for Gordon or Harrison?
Can I ask a very short question? I really like the idea of caching using AST as a key. And I'm just curious to know, do you know like any estimate of cache hit rate? Because you're caching the user's AST, right?
Right. So first, let's you have to keep the context in mind. There was one analysis that was being done on this, and the way I would do it is I'd slowly build up the analysis. I mean, an analysis. This is a long-lived particle search, so it probably took about 1.5 years or so worth of work. And so over time, I steadily built the analysis up, adding more and more plots. So the cache rate, hit rate was extremely high. By the end of the analysis, I was probably making close to 800 plots every time I hit run. And so of those 800 plots, maybe 2 of them actually had to be remade, and all the rest, the 798 or whatever, all came from the cache.
Okay, this is cool. So it's like...
And, so running on the full data set to make 1 plot would take about 10 minutes. To 2 plots would, take 11 minutes. If I needed to remake all 800 plots, that would take 4 or 5 hours. So it was that cache thing was a big deal. But, it's still not fast enough. If you're making 800 plots with this system and you just hit run, it still takes 4 minutes to do all of that cache. And it turns out the reason is that part of what I would do is reweight all of my plots. So I'd first calculate a Monte Carlo data scale as a histogram, and then I'd use that histogram to weight all the other events that I was filling all 800 plots with. And the process of turning that histogram into some sort of hash key, because if the histogram changes, clearly I need to remake all of those plots, was incredibly expensive, and this is because it was root. So, there are obvious places where you can make things more efficient. But this sort of cache is part of what I wanted to enable this exploration, where you do the exploration in the same environment that you do your final analysis. So you're not doing T-tree draw, and then you move over to, now I write my C++, now I go back to T-tree draw. I really wanted to try and combine those two. And I'm actually pretty excited by this. Python is really built with these Jupyter notebooks. Being able to do something like that seems absolutely fantastic to do short explorations slightly more formally than a T-tree draw. And the other thing that I realized while I was doing this is this abstract syntax tree actually gives you the complete query. So for a while, I tried storing the abstract syntax tree in the JPEG that came out of a plot, for example, because not the JPEG, the PNG or the PDF, because you can store extra binary blocks in those pictures. Hackers use this frequently. I swear I wasn't hacking. But wouldn't it be great if you could take a plot from your lab notebook, drop it onto a Jupyter notebook, and it would unroll what the actual query was, and you'd be able to start with the query from just that plot. That sort of operation was in sight. I never made it work completely, but it was in sight in that previous framework. So I think there's lots of opportunities if the AST is expressive enough. That's a question. Can it do everything that we want to do when we make a plot? And that's, we still have, I by no means would claim to have proved that. But certainly for a subset, I think it's correct.
See. Thank you. It was very interesting.
Okay, actually, I have to dash right now, so yeah, this is very interesting, Gordon. So I look forward to having a chat with you if you come to this workshop in May.
Yeah, I'm certainly happy to talk more about the ideas, give more of a high-level talk. I hadn't appreciated exactly what style talk you were going to give, Harrison, so I didn't have time to adjust mine.
Okay. So thank you. Thank you for coming. Seems our speakers need to leave, so.
Okay. Bye-bye.
Bye-bye.
All right, bye.
Bye.